The talk that I brought with me is a talk that I gave yesterday already at a Lean workshop that we just had in Berlin. I guess most people that were at the workshop yesterday, they are now in the other room, which makes sense because I'm going to repeat it. It's actually quite interesting because the workshop yesterday was organized by a person who attended a tutorial on Lean last year at BobConf, and they thought Lean is so great. In 1 year, they went from having no idea and going to a tutorial to let's organize an event, which is great fun. And then some of the speakers were in the same class of people. So I have this presentation. It highlights certain technical aspects of Lean that are relevant if you basically already know that you want to play around with Lean, or if you know similar theory improvers like Acta or Cork and you want to see some differences, then you can also get something out of it. Right now I'm a bit worried because all the people who are already keenly interested in Lean, they probably attended yesterday's workshop, so they are not in the audience now. But I prefer to give my talks for the audience. So essentially, this is an invitation to just send me off on tangents or even normals if you want to. So just make a comment, tempt me to do some live coding. I don't mind if I embarrass myself here. That's fine. It's probably more educating and entertaining that way. If you just let me go and talk, I will talk through this, and it may be interesting to some of you, maybe not all. It's up to you to make it as interesting to you as we can do it together. And the good thing is I didn't prepare slides. I just prepared files in VS Code, so there's nothing stopping us from fiddling around with the things I'm showing you. OK, maybe before I really start, let's get me some idea of the audience. Who has been at the workshop yesterday? I think I see OK, good. Who of you have played around with Lean? OK, maybe a quarter, a third. That's a good start. Who of you have played around with similar systems like Isabelle, Acta, Cork, Idris? OK, great. Now I'm relieved. I mean, nothing wrong with not having done that before, but it really means that we can look at Lean from a different vantage point, of course. You're cordially invited to ask anything about difference between systems. I will try to answer as best as I can. It'll make it more interesting. OK, so what is Lean? Usually we pitch Lean as being two things. It is a general purpose programming language. So this is Lean code. And I probably don't have to ask if you have seen Haskell code at this point. But this looks very much like it could have been Haskell code, right? And it even runs. So let me open the info view, which is this thing on the right, where you can talk with the system. And I can have a little REPL directly in the file. I just say eval, and it evals the thing. And we can see it's opening the file that I gave there, which happens to be the file I'm editing, so you can confirm what I'm doing. And it's calculating a histogram of lines, and it's only printing those that are occurring multiple times. And we see that there are 3 occurrences of Lean in this file as a line. Here's a first tangent I can go on. Since you probably know Haskell, at first glance, this looks like precisely what you would do with Haskell with do notation. On a second glance, you'll see there's some let mute, a mutable let binding. And we see, let me make this a little bit larger maybe. And we see there's some overriding, some assignment here. So this is not recursive definitions Lean, but I still want to highlight this to this audience. So Lean took the do notation that we all love from Haskell, and we now have many languages. And then they added a few more convenient things around it, like what looks like mutable references or mutable variables. It's just syntactic sugar for what you would write in pure Haskell, with just passing pure values around. But it's very convenient. Yes?
So just to ask, the type of the name counts is?
It is the type that we see on the right. So there's no, it's not a type, it's not a first-class reference. This is, maybe we can,
there's a lot of shadowing going on.
So if it weren't for the loop, thinking of it as just shadowing with the same name would be a good approximation of what's happening. The loop here actually gets translated into like a fold-L that passes around some state. So it recognizes which of these values have to be put in an explicit state you would pass around explicitly in Haskell. And we can look at what it actually elaborates to. I'm already going off on tangent here. And we see it's now here we have pure code, and there's a let counts, it's a normal let binding, and it's being passed into this for-in combinator, where it then yields the new value, and that is then taken out. So this is roughly what you would see in Haskell. If you don't see it right away, don't worry. This is a tangent. I'll return now to the main thread of the discussion. But maybe the
just short. So what's the print doing? It's just de-sugars everything, or what?
The print. Okay. I'll defer that question for maybe a few minutes, and we'll have a better time then. What is the key binding in? Okay, this one. Really the point here is that Lean is actually a great programming language for just normal, functional, effectful, getting things done programming. The Lean compiler itself is written in Lean, and just being able to briefly pretend it's imperative and write a do loop, like a for while loop, and have some mutable state and some break locally, completely safe, still everything pure. That already makes it a very interesting programming language, which is not what I want to talk about today. Because Lean is also a theorem prover. So you can write mathematical propositions there, and you can prove them. And here's a simple one. It's Euler's formula for the sum of the first n numbers. I made it easier by reversing this list of numbers before I sum it up for reasons. I will not go into much detail here, but we can prove that the sum of the first n numbers is n times n plus 1 divided by 2. And as you would expect, the proof goes by induction. And then there is some tactic language here that does small step rewriting, it does more complicated rewriting, and it has some specialized tactics for, in this case, solving linear integer arithmetic. And this is the same language. And it's really great to be able to do both things in one language because you can mix and match very nicely. Also, the fact that this is a theorem shouldn't, like, maybe for this audience, I could just make it a def and you would actually feel happier that way. It just shows you that it's the same thing. It's just it's a function that takes a natural number and gives you a proof of that statement. Oh yeah, and as Lean as a theorem prover, and maybe this picks up the question, what does print actually mean? So Lean is a rather big project that has many things, a big system. And there's one component somewhere in the middle. It's called the kernel, which is a very small, rather self-contained thing, which is purely responsible for checking that the proofs are actually correct. And if you look at the proof, I mean, this is not the proof. This is what I told the system to use to construct the proof. If I say sum of n and print it, then I see what is actually being passed to the kernel. And yeah, this is large, and I mean, omega creates huge proofs. So this short thing gets elaborated to this bigger thing. Yes, question?
No. Finish your sentence.
Okay, so Lean, the big system, takes something that is convenient for you to write and turns it into something that can be fed into this little black box called the kernel, which just takes definition, 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 and it tells us, yes, this is good, yes, this is good, yes, this is good. And here the elaboration does something huge. It takes, it runs the metacode to solve arithmetic and creates this huge thing, which then gets checked as the proof. But also this is what happened above, where the surface syntax was extended using a very extensible macro system, almost as extensible as in record, I've heard. Not a record expert here. And this is just like this do notation thing here. Similarly is surface syntax that then gets elaborated to something more low level, something bigger. Okay, no, by the way.
So by now it's 2 questions.
Okay, go ahead.
I mean, you just replace theorem by def, kind of
In one way, like theorem is a bit more restrictive. You can only write theorem if the thing you're actually giving as a statement is a theorem, so something in the universe of propositions rather than values. And then there's some other technical things, like with def, you don't have to give a type annotation before you write the body, and it will be inferred. With theorem, you have to give a complete type before the right-hand side gets looked at. But for our purposes, theorem is a synonym for def.
Okay, thanks. And the second question, I mean, even the proof, and we know how the proof for this simple theorem should look like. I mean, there's a very short proof. Like if you would write this in actor, it wouldn't be much longer than it is. So why does it generate so much stuff? Why aren't they inefficient, the tactics? I mean, if it generates so much stuff.
So in this case, it's extreme because omega is this Pressburg arithmetic decision procedure. So it can solve any kind of goal that happens to be using a certain fragment of math. And it's doing some rather elaborate process of turning it into some internal data structure, proving something there, relating it to the goal. So it's a bit like shooting with cannons on. Well, I wouldn't say it's a sledgehammer because sledgehammer is a specific tactic in Isabel and will confuse people horribly. Yes, it's a very powerful hammer for a specific thing, and it's a bit, maybe too. But it's still, it's just so convenient to see. Okay, I have a goal, and I know the rest is just simple arithmetic, and I just write omega, and it works. I don't have to think about which way do I have to annotate, like associate my addition so that it goes through, as I maybe have to do in Acta. Okay, I need to be careful not to say too many wrong things about Acta here, because we have experts in the audience. Okay, this was the brief intro to what lean is. I actually need to. Let's just revert. Hot take: lean does not have recursive definitions. That's maybe shocking to this audience because how can you do anything useful without recursion as a functional programmer? Now, I guess I already hinted at this. Lean is both this big thing that you interact with as a user, but lean could also be considered the kernel, the component that implements the logic that is underlying the theorem prover. And if I say lean does not have recursive definitions, I mean the logic, like the type theory that lean is based on, is a variant where there is no recursion. This is different in Acta or Coq, as far as I can tell, where recursion is a concept that is known to this kernel thingy. In lean, it isn't. And the kernel will reject recursive differences. It will not accept them. Now, lean, the system as a whole, usually tries really hard to shield you from things that the kernel will complain about. So it will only it will elaborate things that are correct and then pass them to the kernel for double checking. But lean is extensible. So earlier today, I wrote this little command, simpledef, which is like def, but it does less elaboration. So you basically get to write things more rawly, and then pass them to the kernel and see what happens. And I can use this to define a function that returns the successor of an argument. But if I try to write a recursive function with this thing, it will complain. And actually, this guard message thing, let me just remove that. This is just a way of basically embedding tests into your code or assertions about the behavior. So if I just write this, I get an error message, and I can look at the info view, and it tells me what's wrong, or I can look at the hover. Often it is very useful to be able to write this guard message here, and this basically asserts that this command has this output, and if the output changes, it will complain, and there's even a code action to update. Very, very convenient to write tests inside your code or just quickly check something. Okay, I went off on a tangent. Okay, so lean, the kernel, doesn't have recursive definitions. Why is that important? It's important because we want a theorem prover to be sound. Sound meaning you can only prove things that are true. In particular, you cannot prove false. The statement of absurdity, if you prove that, then you can prove anything, and then it's no longer a useful theorem prover. It may still be useful for other things. I mean, dependent Haskell has its uses, but it's not a theorem prover. And why is recursion so bad? Most of you probably saw this, but let's imagine I could define something recursive. Then I could actually make a theorem. Maybe I should have called theorem here. That takes some proposition, that want to do anything, and gives me a proof of that proposition by calling itself. Circular reasoning. Die Schuldenbremse ist gut, weil die Schuldenbremse gut ist. That's a circular argument. And that's why the lean kernel at least shouldn't allow arbitrary recursion. Now the other systems, Cork, Acta, they get away with having a termination checker inside the kernel that will allow certain kind of termination, certain kinds of recursions that are still okay. But it's a complex logic that's now in the trusted code base, and the lean developers decided, let's keep the kernel lean, one reason why it's called that way, and define it so that the kernel doesn't even have to deal with this termination problem. But then how do we define the recursive things? I mean, we want to define recursive functions, clearly. So maybe actually I'll reorder this. Quick recap, most of you will have seen it. Oh, who has seen this definition of natural numbers before? Okay, inductive definition of natural numbers, that's how we define them in lean. That's fine, okay. Sorry, Julius, I'll explain it to you later. And clearly we want to write addition that way. This is our natural definition of addition. We look at the first number. If it's 0, we return the second argument. If it's a successor of something, we return the successor of adding this number to b. And that's a recursive definition. We can't define this directly to the kernel because the kernel doesn't support recursion. What the kernel supports, however, are recursors. Different thing. So this is the definition of natural numbers that we find in the library. I've just put it in the namespace so that we don't get an error about duplicate definitions here. And whenever the kernel, or whenever the system sees, I can say the kernel, whenever the kernel gets told to, like, please define this inductive data type, it will not only define the data type and the constructors as symbols in your environment, but also create out of nowhere, as an axiom, so to say, although maybe I shouldn't say this dangerous sounding word, a recursor. And it has a type like a function, so I can call it. And it allows me to construct things, it allows me to construct functions from the natural numbers by giving essentially the two cases that we often want. I can tell what it should be if it's 0 and what it should do if the argument is a successor. And here we get the result of our thing we want to define for the smaller number. So essentially, okay, for the Haskell programmers, that's just the folder of our data structure, or the catamorphism for those who like long words. For those who've been to high school, it very much looks like normal induction on natural numbers, and that's precisely what it is, only that it's not just for defining theorems, but also for defining data, for defining functions. Yes, please.
Yeah, so it is like an axiom in a sense.
Yes. Yeah. I guess the difference is it is a systematic construction for every inductive data type. So it's part of the inherent rules of this type theory that for every time you define some inductive like this, you get that. Whereas an axiom, at least one could use the word for the things you just add on top, like the axiom of excluded third.
The way I like to see it is that there is some sort of meta rule that says whenever you have an inductive data type that is not too crazy, you can write crazy things in there, then it no longer works. If you add this axiom, then the result theory is still consistent.
You could say so, or you could say it's a meta rule that says whenever you have inductive type in the environment that has been satisfying all the rules for that, you also have this in the environment, and then it just becomes part of your meta language of.
Yes, exactly. And the point is that you want to know that the axiom does not introduce any contradictions.
Right. Right. Yeah. And because and I guess also the difference is maybe the kernel gives me this. An axiom I can just give to the kernel, and it'll just accept it. Okay, with this we can define addition. Basically, we saw the correspondence between the arguments to the recursor and what we want to do here, so I just put the cases in here and here. And now I have defined additional natural numbers without using any recursion, because I was using the recursor. And it works. We can use guard message again, but we can also see that this is actually some, 35, some interactive thing. Yes, please.
Sorry, so the kernel knows inductive data types?
Yeah.
Or
Yeah.
it elaborates into the recursor?
The kernel knows inductive data types and constructs the type of the recursor for you, and also internally knows how this recursor behaves, how it reduces. So it not only gives you some, like, there exists a function with this type, but it also knows that if you apply the recursor to 0, it should return this thing. And this way, the reduction actually works.
I mean, it's just a manifestation of the fact that an initial thing is actually initial, right? I mean,
Yes. Yeah. That's another way of putting it.
I mean, when comparing to ACTA, I think this is a good point. In ACTA, you currently rely on it on much more than just the kernel.
Well, I would say the kernel of ACTA is larger because it has, for example, the termination checker as part of the trusted code base.
What's this motive thing? What's this?
Good question. As I said, the recursor, you can define theorems with it, you can define functions with it, and because Lean is a dependent type language, oh, I should have mentioned that. It's already so normal for me. A function that takes a natural number the type can refer to t, can refer to the number. So, for example, the function, like you have a type of vectors of length n, and you have a function that like replicates some value n times, then the result of that will be vector n. And then if I were to do this with the recursor, then the motive would be vector of n, like of length n. Or if I use it to actually define a theorem, then the motive here could be something complicated like t squared plus minus t squared is t plus 1 minus some statement.
the U is a universe number?
Yes. Yes. But maybe I'll not go on off that tangent now. Okay. So Lean has no recursion. Lean has recursors, and we can, if we want to be very primitive, very fitting, define our functions using the recursor directly. But of course, this is tedious. Like we don't want to write this. We want to write something like this. And because Lean is also the bigger system that helps you prepare the stuff you write for the kernel, you can do that. And this is the first class of recursive definitions we want to look at, namely structure recursion. And basically, this means that the function that I just had in a comment, because I didn't dare to write it, I can just write it. And Lean will accept it and will translate into a form that the kernel will accept. And it will do the things it should. We can look under the hood. We've already seen how to do that. We can use the print command. And if we do that, we see that it's elaborated to something larger again. It's a theme we recognize. It's actually not doing something with nat.rec. There's something called nat.brec on, which is not what we just saw. But actually, nat.brec on itself is another definition. So it's not part of the kernel. It's part of the system around. And this definition, I will not go into much detail of what it does, but it's defined using the recursor. So my statement that it gets boiled down to using the recursor for natural numbers is still true. I will hide this before you get too confused by the internals here. But one of the reasons why it's not just using the recursor directly is that Lean allows not just primitive recursion. So just from the terminology of this talk at least, primitive recursion is something like this, where you have, well, you immediately pattern match on the parameter, and then you recurse on the immediate subcomponent of the constructor. And many functions are primitively recursive, but not all. And the biggest, well, maybe not the biggest, but the most prominent example, for examples at least, is the Fibonacci number as defined as a recursive function. And here we see we can do a bit more complicated pattern matching. So we first pattern match on 0 and on 1, and only if it's n plus 2. I could have written n plus 2, but I'm trying to be more explicit here. If it's n plus 2, then I do a recursive call. And I actually do 2 recursive calls on the immediate subcomponent of my argument and like one further in. And this is not primitive recursion. It wouldn't fit the net.rec scheme. And if you actually try, I mean, you can try to define it with net.rec, that you will find a way with some like helper definitions and things, but it's tedious. So this is one of the things that lean as the system does for you. It allows this more general kind of recursion and finds a way of compiling it down. The keyword here is cause of value recursion, and you can imagine it's a bit like memoization. So it's instead of just doing the primitive recursion, so going one step down, it calculates all the values. I mean, not effectively, not while running the program, but logically, calculates all the values up to your argument, and therefore you can, when you deconstruct the argument, also recurse on like things further in. Usually you don't think about this, like it just works. You know, you pattern match, you do a recursive call, everybody's happy. Small another note, another addition where Lean does something under the hood to make you happy. And since I've implemented it, and I wanted to keep it on the slides, you can actually do mutual recursion. So we have 2 functions, even though they call each other. They are both structurally recursive. So the recursive call is on smaller arguments, or like in subcomponents of the arguments. But now there are 2 functions involved, but the recursor only gives you 1 function. OK, there's a little bit of construction you can do under the hood, and Lean does that for you automatically. Small convenience. This is what I would want to show you about structure recursion. Any questions at this point? The question rate has dropped drastically when I went to the second slide. So, yes, thanks.
Yeah, actually, so I think this might be related to the previous file. So you did like a print of this elaboration, and then you showed us how one of the values that was used there has a further elaboration. So how does it? So somewhere in like, I don't know, I guess there's supposed to be some like meta programming keyword or something that gives you like several stages of deliberation, and then print only prints you the first level or something?
No, print gives you the end result. It's just basically there's an intermediate definition involved, and I looked at both of them.
Why wasn't that substituted?
Why should it?
Okay. Fair enough.
I mean, it just makes things larger in the environment. Okay.
So there's nothing special. Okay.
No. Yes, Manuel.
What if your recursion is not structural?
Oh, good question. Let me then continue with the talk. Yeah, OK. So OK, Manuel might want to define recursive functions that are not structurally recursive. What did he just say to Sniper? Like GCD. It's not the example I have on the slides. It's not that good. But OK, so here's, I mean, I said Lean is great for programming. And one of the things you do with programming often is you have arrays. And when you go through arrays, you use with indices. And then code like this is somewhat idiomatic. So here I check whether all elements in an array are the same value. And I do this rather pedestrian style. No higher order function here, just for demonstration. So I check whether the index is still in bounds for the array. If it's not, then true. If it is, then I check whether it's the element equals to the first element in the array. If it's not, then I return false. If it is, then I do a recursive call. So I'm just implementing a loop as a recursive function. Nothing surprising here. And of course, I increase the index by 1. Now, this is clearly not a structurally recursive function. I'm not pattern matching on anything. This number gets larger, not smaller. but it's also clearly a terminating function, because eventually we'll hit the size of the array, and then everything is fine. And I can do this in Lean. It just requires a different machinery. It requires that of well-founded recursion. And in order to do that, I have to tell Lean about two things. I have to give what's called the termination measure, namely or maybe one step back. Why do I think that this terminates? If I want to explain to somebody why this is a terminating function, I say, well, look, the difference between I and the length of the list gets smaller every time. And also a difference is a natural number. They can't get smaller forever. Like it's not a real number where you can have approximation. It's not a integer where you can go with negative numbers. No, it's a very nice natural number. And these have this nice property that you can't start with a natural number and go to smaller numbers forever. Eventually, you'll stop. And that's the core of many, many termination proofs. So I can explain the same thing to Lean, and I do this in two steps. I say this function is terminating because of this measure here, which is the difference between the size of the array and the parameter. And then I also have to actually prove that this is actually getting smaller. So if we look at, now we're in proof mode. We didn't actually see much proof modes yet. So here I can write tactics like we saw on the first or second slide. Here on the right, we see what we actually have to prove at the moment, the goal state, and we see that we currently have to prove this thing, and these are some assumptions we can make, something we assume to be true in the current proof. And we see, for example, that we have to prove that something is smaller than the termination measure that I just specified, with I being the parameter of the function. And what is smaller? Well, it's still, again, our termination measure, but now with the argument of the recursive call, I plus 1. So this is what I just said would be the requirement for the measure gets smaller in the call. And this actually can be proven because very conveniently we have in the context the fact that I is actually smaller than the size. If this wouldn't be the case, then maybe this would already be 0, and then this would also be 0. Like the difference would be capped at 0, and it wouldn't get smaller. So it's very important to see here that I is less than the area, the size of the array. And again, some arithmetic proof. It's probably a lemma I could use, but I don't want to think about which lemma to use, so I just use, again, omega, and it proves this for me. And this is the general. Oh, wow. Yeah. This is the general scheme of recursive proofs using well-founded recursion, which is a very powerful method because you can do very complex things here. Just last night after the workshop at dinner, I don't think he's here. We played around with some very interesting recursion pattern. We had like a 3-tuple of things, and never mind. It can be more than a natural number. It could be like multiple things, and you can have lexicographic ordering. Right. So this is, in a way, the much more general way of doing recursion in Lean. More powerful, but also more involved. Question? Yes, please.
Yeah, sorry if I just asked syntax question.
Please go ahead.
In line 13, it's like this condition is a proposition now. What? I mean, it's like it's not just evaluating to some boolean. But in line 14, it is just boolean, or what is it? I mean, or is it also a proposition?
Lean converts between propositions and booleans as necessary. So in fact, the if then else takes a proposition. So these are propositions, both equals and less than a proposition. Like, the Boolean one would be the double equal. But it only accepts, at least when you want to compile the code, decidable propositions for which it knows how to decide them. And usually while programming, it doesn't really matter which one you use. So good question. The underscore here, actually I could give it a name here. This gives the name to the thing, and if you were to look at the proof state, we will see now it now has a name. If I were to leave it out, then this will show off nice features of Lean. It will actually complain about the array indices because now it doesn't know anymore. Like now this doesn't have a name anymore. It's not in the context, so to say. And then lean cannot prove that this I here is actually in scope. I could do things like, well, just try anyway and give and throw an error at runtime if it fails, like in most languages. The termination proof still goes through because here, for technical reasons, we still get it into the context. So for array indexing, we have to explicitly say I want to have the condition of the if and else available. For the termination proofs, you get it for free. Yeah, but this whole array, like automatic proving of array indices, it's also a very nice thing for using lean for general purpose programming. Yes?
While we're at it, could you also leave out the inner if?
The inner if, I mean, that would just make it.
No, I mean, and then return array I equals this array 0 and all are same?
Probably, yes. I think I just wanted to make it, yeah.
Clearer.
I just wanted to make it clearer, but this works well.
While we're at
Yeah.
syntactic questions. Then it's okay to have it as a proposition, or do you need to turn it into Boolean?
It gets automatically,
Oh, okay.
there's like inserts the right coercions. Okay. What I would definitely don't want to let you go thinking that once you have something slightly more complicated in structured recursion, you have to write all these things. So let me demonstrate that at least in many cases, lean is able to just guess the right termination proof, and it's also able to guess the right termination measure. So you can just write this and it'll be accepted. So many, and this is also it's a quite neat trick because I mean, it wouldn't be so surprising to find a termination measure that happens to be one of the parameters, but it's finding a relatively complex expression, and we can actually check that it really finds this one. So we can ask which termination measure did you find, and it finds the one that we gave. And we can actually make it explicit again. Sorry. Oh, I didn't want to open Copilot. So there's lots of convenience around that you don't always have to do this. Yes, next first species.
Atomic bomb question. Can you define the Ackermann function?
Okay, yes. And it infers the measure automatically because it also tries lexicographic combinations. Again, my pull request. Hey. Yes, so this is what I referred to with briefly mentioned. You can actually have more complicated measures that are lexicographic. So every recursive call decreases A, or A stays the same and B decreases. Powerful technique. Okay, we have 5 more minutes. I will skip partial fixed point. It's scary anyway because you suddenly are defining functions that are really not terminating, and it still kind of makes sense. Too much for 5 minutes, but talk to me later or Google it. It's fun. I will briefly mention this because we saw the structure recursion being, okay, this is nice and easy when it fits, but we also saw the well-founded recursion, also often convenient because automatic and much more powerful. So why do we even have structure recursion? Why not always use well-founded recursion? The 2 reasons, I guess, the structure recursion, you don't need an explicit proof. Even if you don't have to find it manually, it still means it's being found by the system, may make things large and slow. But the more important one is structural recursion has good kernel reduction behavior. So dependent type programming requires, when checking whether 2 types are the same, you may have to run a function a little bit, or all the way, or symbolically. Like knowing that, what's a good example? 0 plus 1 is 0. 0 plus A is A. This is something that may come up in dependent programming. I will skip the example now. And this only works if the addition is actually defined using structure recursion. Well-founded recursion you cannot really use when you want to define types, so don't even try, or when you want to rely on kernel computation. So the proofs by reflection techniques, just dropping the name here, avoid well-founded recursion. So it makes sense to have both. Okay, I mentioned I will skip partial fixed point. I can define the f91 function if people know the f91 function. If you don't know, you can Google it and then be amazed that we can define it. I think I've explained most things about compiler versus kernel. Maybe 30 seconds fact here. Explained Lean is both a theorem prover. We discussed mostly the theorem proving aspects. It's also a programming language. So there's a normal compiler, just like in Haskell. It does the same things as a Haskell compiler does. Spits out a binary at the end. And to that compiler, all these are the same. Because the compiler supports recursion, so it basically branches off the pipeline before we even start removing the recursion. So it doesn't matter how you prove the system, like the existence of the function to the kernel, it gets compiled all the same. Okay, what questions do you have before we run out of time? Please go ahead.
Well, my question is, am I the only person in the room who has never seen any theorem proof before? And if not, could you show me some of the basics, please? Like, why would I want this at all? And for instance, that first snippet where overview came up, I'd like to know, that's all Greek to me, I'd like to know what any of that meant.
I didn't catch all of that. I guess one part of the question is why would you even care about a theorem prover?
Yeah, that's one thing, and also just some basics for those who have never used any theorem proof.
Right. So one application is you can do proofs. If you're mathematicians and you write your proofs and you're sick of writing proofs on paper because you keep getting the indices wrong, or people don't want to read your papers, but you still want to know whether they're correct, you can use a theorem prover because it allows you to write the proofs in this language of Lean, and it will tell you whether they're correct or wrong.
But I mean, why that already exists, there's many of them, but why have it combined in a general purpose programming language?
I think one of the reasons is that it's sometimes nice to use a little bit of this logic reasoning within the program. So one practical example is what we saw here, where it's doing proving here to prove that this I is actually in, I mean, for this one, it's not so surprising. I is less than the array size, okay, that's in scope. But it can also deduce that the 0 is in scope. And there's already some mathematical reasoning happening here, if you think about it.
Isn't it sort of the other way around as in Isabel, where it took them like 20 years to discover they actually want to generate programs out of their proof? And here it's just like that from the start?
Maybe, although I think given that Coq is the most closest relative to Lean, I would say, it's not so surprising. I mean, we have iterates and things. So I think the idea of you want to have all these nice types in your language, it's not so far off. Okay, we have run out of time. Thank you all for the questions. I think you made it an interesting session. So thanks for that. And I'm around for more questions in the break or afterwards, and for dinner especially.